Okay, hi physics team. We're on to accelerators. And what do accelerators do? Accelerators are machines which accelerate charged particles. So I want to just correct that. Accelerators accelerate charged particles. And we're going to look at accelerators using our knowledge of electric fields and magnetic fields. And we're going to advance in order of increasing complexity, which really means we advance along with the history of development of these machines. Now, if you were interested in the history of development of these machines, you could, for your bedtime reading, enjoy reading a wonderful book like The Particle Explosion by Frank Close, Michael Martin and Christine Sutton, one of my favourites. No doubt you'll be all on Amazon or trying to find your second-hand copy of that little gem. Now, moving on. Just as a little historical aside, before we had accelerators, physicists went to the top of mountains because they managed to notice that there were a lot of cosmic rays there and you could capture them in primitive detectors, primitive cloud chambers. And and places where they did this were the Pic du Midi d'Ossau in France and Pikes Peak in Colorado. And both of those places now feature fantastic mountain roads. So if you're looking for somewhere to ride your bike or drive a car or a motorbike or somewhere, both those roads are now very, very popular. So let's start off with the linear accelerator. Now the popular picture that appears in the book is the one at Stanford in California, which is called the Stanford Linear Accelerator, or SLAC. And a linear accelerator is very much building on what we already know. So let's have a look here. Imagine I've got a proton, and we know from our earlier work that if I connect this to a sort of high positive voltage, and we've got a 6,000 volt supply in the blue box in the cupboard, and I connect this to what in relative terms is a negative voltage, then there's going to be, maybe to make that work, I'd be better off having this as say minus 6,000 volts, if I could rig that up. And then I'd have double the potential difference. So now I've got my proton moving through a potential difference of 12,000 volts from plus 6 to minus 6,000. Okay, so we're happy that this is going to accelerate in a straight line, whoosh, and we've done the maths so that we know when it gets to here, it will have a certain speed. We've done that. Its kinetic energy will equal the charge on the proton, which is the same as the charge on the electron, times by the voltage we accelerate it through. So in this case, we'd be looking at it being 1.6 times 10 to the minus 19 times by 12,000 volts. And that would be its kinetic energy. And we could then rearrange and say, okay, once we've found this kinetic energy, that kinetic energy also equals half mv squared. And then if we put the mass of the proton in there, so that's our mp for mass of proton, we could solve for a velocity and find out how fast it would be going. And presumably it'd be going quite fast, and that would be great. But the problem with that is it's a bit of a one-hit wonder. So wouldn't it be better if we could somehow pile those up in a line and preferably use the same voltage supply to make it a little bit simpler? So how do we do that? We pile it up in a line by making a linear accelerator. So here's my attempt at linear accelerator. I just want to we'll deal with all that rubbish later. So now, I know what you're thinking. It doesn't look like much. And the reality is, I've forgotten to mention in our last lesson that whenever you're making all these machines that accelerate things, you've got to get the air out. And then you've got to have some sort of, all your equipment is going to have to be contained in a surface that's strong, that you can suck all the air out of, because obviously you can't accelerate particles if they're going to bang into air molecules. So you've got to completely clear it out. Now, when you make a linear accelerator, you do it using fairly large copper cylinders. So I started off trying to make a three-dimensional linear accelerator. And And I thought, yeah, that's interesting. Now, so what happens is, let's say we're starting off with a proton. So it is all hoops and it is all evacuated, but let's just keep it simple. So let's say I'm starting off my proton here. Now, I need it to accelerate it from whatever the source of the protons is. I need it to come towards the first thing. So what I need to do is have a negative voltage. And the way we do this is by having sort of sections of voltage that can be switched on and off. And so a lot of the making particle accelerators is sorting out these in big high voltages to switch quickly and to be under control at great speed. So in this case, we're going to have a simple alternating current. So we're going to start off and we have a negative voltage here, which attracts this towards the plate. So our proton's now accelerated. And then as it approaches and is in the middle of this cylinder, shall we say, we could do with magically switching it so that it now gets repelled by that cylinder and attracted to this next cylinder. And then as it's in that next cylinder, we could do with switching it so that, where have I got to now? I need to attract it, so that, like this, so that now it's repelled. Bear in mind, it's going to have its momentum, so it's going to be keeping moving. Now repelled and attracted to the next cylinder, which is negative. And then I need to have some other arrangement of these switching cables so that as soon as it arrives being attracted to a negatively charged cylinder, that then is switched to become positively charged to repel it, to push it on. Now, each time this happens, it accelerates through the same voltage. Because we're just switching, we're actually just doing a regular sort of backwards and forward switching. So we're just kind of going like that, and then like that, and then like that, and then like that. So we're just switching backwards and forwards. And we're going to have obviously very long arrangements like this. And as it goes faster, because this switching is at a fixed rate, you have to have longer pieces of copper, so longer cylinders. And that's because you do it with a standard alternating current where you don't change the frequency of the alternating current. Anyway, that's probably going a bit too far. So don't worry too much about the switching idea. Ultimately, we always have it being repelled from the cylinder it's in and attracted to the next cylinder. And every time it goes through a gap between the cylinders, it gets accelerated by the voltage. So we can have lots and lots of goes at accelerating it, which makes it much, much better than having just one go. So with a linear accelerator, we can really make things go much faster. Now, key points from this. 1, the particles move in a straight line. They're accelerated by electric fields, and a switching of the large voltage is needed, but the frequency of that switching is normally fixed. So that's relatively straightforward. Proton, attract to the negative one, make this one positive, this one negative, attract, make this one positive, repel, attract, and just keep, and every time it's going faster, every time it jumps, it gains kinetic energy because it moves through that field. Right, on to the next one. Now, the cyclotron. Okay, you are going to make your own cyclotron as part of today's lesson challenge. And we need to go through what you need. First of all, you need some cardboard. So, cardboard. Okay. Oh, I've got the wrong page. Crazy. Do apologise. You need cardboard. You need scissors. You need a ruler. And probably some coloured pens and a few bits of paper or anything that you can improvise into these rolls. Okay. Now, stage 1 is to make the thing called the D. Now, because these were invented by Americans, I don't know if that's an American thing, but they gave them fairly straightforward names. So we need to make a big semicircle. Now, for those of you who are not mathematical geniuses, my trick for making a semicircle was to just draw a circle and cut it out because I am a genius. And that's how it worked. So I thought, there must be a better way. So the better way is to use your ruler to make a little guide and then mark a series of marks to follow where you're always marking it at 10 centimeters. I know this is the rocket science bit for people. Now, you might say, sir, this video is really dragging on a bit, it's getting a bit dull. Oh, but let's skip that because here's one I made earlier. Marvelous. So, I now have a D and 2. So, step 1, make the Ds. Arrange the Ds. So maybe you have a look at that and keep that on your, freeze that and keep that on your screen while you're sorting out what you're doing. Right, let's get on with going through that list then. So if I have that list in front of me, here I'm making my cyclotron. And the Ds need to be arranged so that they are a little distance apart and your source of protons is magically in the middle. Remember that the Ds are actually 3-dimensional, so they're actually invented as little boxes like this. If you look at Lawrence's original one, which is about only a little bit bigger than this. Anyway, so, and they're slightly offset. So if you can see that I start with them perfectly in alignment and then I want them slightly offset so that one projects out. Okay, because I'm going to need that at the end. Okay, so I have to decide now that which way I'm having a magnetic field. And for the benefit of the video, I'm having a magnetic field going down into the page. So I'll just leave that there throughout the whole thing, which means that when proton, positively charged particle, when I get my fingers out, positively charged particle left hand, I'm going to always be pointing down because my field is going down into the page. Okay. What else is on the list? Decide on the magnetic field direction. Place the proton in the middle. I'll use this pen top to be my proton. Sort out the positive voltage and negative voltage signs. So I've made 2 little signs for myself. Okay, and if I start off like that, I can make a start and say my proton is starting off here in the source of protons, a mysterious object. And if there's a negative voltage here, it will immediately be accelerated into this D. Okay. It's accelerated into the D. Now, once it's in there, it's going to, all the time actually, it's going to experience a force. So, it's going this way at the moment. So, first finger field, down. Particle motion is the second finger current. So the force is towards the middle. So it's going to experience a force this way. So the force is that way, which means it's going to follow a curved path and go around. Now, if you imagine it's traveling, first finger field, if you imagine it's traveling that way, then the force will be to the center of the circle again. So when it's here, if you get your fingers out and check that out, the force will be going that way. Now we've got to the gap. Now we need to time this so that at this point, the voltage supply switches. Perfect. So now we can now accelerate across this gap and be traveling faster. Now, because we're traveling faster, we'll experience the same force towards the center of the circle, but we'll travel in a wider circle because we're going faster. Then we'll get to the edge of the D again. Need to switch the voltage. Notice that we never switch this. When we look in detail about how you make it, that'll be obvious. So remember, all the way around here, we had forces towards the middle of the apparatus that kept our proton beam. So whoosh, accelerate across the particle, across the gap. Attracted to the negative, repelled by the positive, whoosh. Faster. Same force directions all the way around. That's what's generated this, is a force towards the center of the circle. And then we go on and on, remembering that every time we do a semicircle, your path to jump from one D to the other, Did I forget a switch? Did I forget? To jump from one D to the other, we have to switch the voltage. And then it accelerates across the gap. So our electric field accelerates, and our magnetic field keeps the proton moving in a circle. Okay, so our magnetic field, okay, so now I've jumped again, ever faster, and jumped again. And jumped again. And every time we go from one D to the other D, we have to jump. And then at some point at the end, it's going fast enough to get to this point where it escapes the apparatus. And that's the whole point of a particle accelerator, is you want to do something with this particle. Okay? You want to do something with it. So at the end of a particle, and the particle collisions that we're going to then look at are the kind of thing you'd look at in higher physics. Sorry, in physics at a higher level, perhaps at university, etc. Okay, so that's how the cyclotron works, and I'd like to see a picture of yours working your intact and beautiful cyclotron. Now, before we finish, the one thing I wanted to say is the actual practical considerations of making a cyclotron are not to be sniffed at. To make this magical magnetic field that I was talking about, you're going to need a huge coil. That coil is going to then generate a magnetic field which will be nice and regular going through your, so there'll be magnetic field lines through these huge coils, and you need them to give you a regular magnetic field through the apparatus, okay? So you're going to need huge coils. Now, and to make this apparatus reasonably large, you're going to need a very, very strong magnetic field. So strong that in the original ones, they had to wrap these coils had to be wrapped in water, in a water jacket to keep them cool. So you've got a very high current coil creating very strong magnetic fields, which is wrapped in a water jacket, and it has this completely, you've got an electrical supply system, and then you've got a cooling water supply system. And then, as well as having, so you've got your direct current supply to these electromagnets that are going to create a huge magnetic field for you. And then you've got to remember that your actual apparatus, your cyclotron, is going to have to be in an evacuated case. So that's going to have to be wrapped in a very tight system where because we can't have any air, we've got enormous electric currents, water, particles, and we've suddenly got a very complicated machine. But the basics of it are a magnetic field and an alternating electric field. So if we can understand that, that will tick the box for cyclotron. Now I'm going to stop there, and we'll go and do synchrotron another time.